Hello everyone, welcome to our channel. This is Dinesh MA, working as Assistant Professor in the Department of Electronics and Communication Engineering, Maharaja Institute of Technology, Mysore. In the last session, we understood the working of the inverting amplifier, non-inverting amplifier and summing amplifier circuits. In this session, we will discuss few more applications of op-amp. Among that, the very first one we are considering is the difference amplifier or subtractor. As we can see here in the circuit, the difference amplifier has got two inputs, VA and VB. So essentially this circuit would be providing the difference of these two signals. So V0 is expected to be VB minus VA, as VB is connected to non-inverting terminal V1 and VA is connected to inverting terminal V2. Now because we have two input sources connected to two different input terminals, we will be using superposition theorem, which allows us to determine the outputs considering one input at a time. So using this, using superposition theorem, we can write V0 is equal to V0A plus V0B, where V0A is the output considering VA input alone and V0B is the output considering VB input alone. Let us determine the output expressions for V0A and V0B. Considering VA alone, this one, looking at the circuit, if I consider VA alone, VB should be grounded. So the op-amp circuit works as an inverting amplifier. So V0 for an inverting amplifier is given by minus RF by R1 into Vin, whereas V0 is V0A and Vin is VA. Therefore, V0 can be written as V0A can be written as minus RF by R1 into VA. So this is the expression what we have for V0A. Likewise, we will consider VB alone. Considering VB alone, in this circuit, VA should be grounded when we consider VB alone. Then the circuit will be working as a non-inverting amplifier, where V0 is given by 1 plus RF by R1 into Vin, where V0 is V0B and Vin is this terminal V2, which is nothing but V1 because of the virtual short concept. Now looking at the circuit, V1 can be determined by using voltage divider rule. So V1 is equal to, here V1 is given by VB into RF divided by R1 plus RF. So V1, let us put this as VB into RF divided by R1 plus RF, so that V0B will be equal to 1 plus Rf by R1 into Rf by R1 plus Rf into Vb, right? So this can also be written as V naught B is equal to, by considering this, rewriting this as R1 plus Rf divided by R1 into Rf by R1 plus Rf into Vb. Now these things can be cancelled. Now what we have is V naught B is equal to Rf by R1 into Vb. So now we have the expression for V naught A and also V naught B. Let us substitute these two in this expression. So let me rewrite this as this, and V naught, now V naught is given by this one minus Rf by R1 into Va, and this one plus Rf by R1 into Vb. So where V naught can be written as Rf by R1 into Vb minus Va. So now if we equate Rf and R1 value, then V naught will be equal to Vb minus Va. So what we can see here is, so the output voltage is equal to the difference of the two input voltages Va and Vb, because Vb is applied to the non-inverting terminal and Va is applied to inverting terminal. The output voltage is given by Vb minus Va. So this is the working of the difference amplifier or subtractor. Now let us understand the working of the op-amp integrator circuit. Now this is the circuit diagram what we have for the integrator, and here we can see the input signal Vin is applied to the inverting terminal V2 through input element R1, through which current I1 is flowing, and non-inverting terminal V1 has been grounded, and capacitor C has been used as the feedback element, and the current I1 which is coming through R1 cannot get into the op-amp because of the high input impedance, and this will be flowing through the feedback path charging this capacitance, and we'll call this current as If. So I1 is equal to If. Let us equate these two. I1 equals to If, and let us put up the values or the equation for I1 and If. By using Ohm's law, I1 can be written as here Vin minus V2 divided by R1, and V2 is approximately equal to V1 because of the virtual short concept, and V1 is equal to 0, so V2 will also be equal to 0. So I1 is equal to Vin by R1. So this is the expression what we have for I1. Now coming to the feedback path If, which is charging this capacitance C. So this can be written as C into d by dt of the potential difference, that is V2 minus V0, and V2 is approximately equal to V1 which is equal to 0. So If is equal to minus C into d by dt of V0. Now let us equate I1 and IF. So this is going to be V in by R1, which is equal to minus C into d by dt of V naught. So now V naught can be written as d by dt of V naught is equal to minus C into this R1 into V in. So now what we have is d by dt of V naught, and what we need is V naught. So what we'll do is we'll integrate both the sides with respect to time. So what we can put up here is integration d by dt V naught with respect to time is equal to integration of minus C into R1 into V in with respect to time, right? So now here we have the integration and the differentiation. So these things cancels and we are left out with V naught. So V naught is given by this C and R1. These two are the constant values. With the negative sign, we'll keep these out of the integration. So minus R1 into C integration of V in with respect to time. So this is the expression for the output voltage of the integrated circuit. So what we have is there is a gain which is given by R1 into C, and negative sign indicates the out of phase signal and the integration of V in with respect to time, and the same thing has been shown in the output waveform with respect to the inputs. So this is the working of integrator circuit. The next circuit we have for the discussion is op-amp differentiator. And this is the circuit diagram for the op-amp differentiator. As we can see here, the input element is capacitor and the feedback element is the resistance. The input signal V in is applied to the inverting terminal V2, whereas the non-inverting terminal V1 has been grounded. And the current I1 is charging the capacitor C, and this I1 cannot enter into the op-amp circuit because of the high input impedance, and this current will be flowing as IF through the feedback path. So I1 is equal to IF. So let us write I1 is equal to IF, and writing the expression for I1 using Ohm's law. So this I1 is charging this capacitor C, so this can be written as C into d by dt of V in minus V2, and we know V2 is virtually connected to V1. So V2 is going to be 0. So I1 is equal to C into d by dt of V in. And let us put up the expression for IF. So IF is given by V2 minus V naught divided by RF. So V2 minus V naught divided by R, and V2 is equal to 0. So IF can be written as minus V naught divided by R. So let us equate these two equations. So minus V naught by R is equal to C into d by dt of V in. So V naught can be written as V naught is equal to minus R, this R goes here, into C into d by dt of V in. So this is the expression what we have for V naught. So here we can see output voltage V naught is given by differentiation of the input voltage multiplied by the gain factor given by the resistive element and the capacitive element with the negative sign. So again, negative sign we have because op-amp is connected in the inverting mode, and this is the input waveform and output waveform for the differentiator. So all we have for this session. So in this session we have discussed 3 applications like the difference amplifier, op-amp integrator and op-amp differentiator circuits. Thank you.